Hello, today's lecture, Lecture 3 on Atmosphere and Weather, is all about what is climate. Climate is basically not what's happening right now, that's weather, but it's what's happening over a 30-year period. We may be having a very, very wet year in Southern California or a very, very dry year in Southern California, but that's what the weather is over a long period of time that gives us different ideas. The other thing that the two main factors that determine the climate is what is the average temperature over that period of time and what is the amount and distribution of precipitation in that area for that climate. So another thing that affects it is its latitude. Now, remember, latitude is like a hat. It has to do with these things right here. So that's what your hat goes down to. That's latitude. And if you look at this picture, it's fairly obvious that at the equator, the middle of it, the temperature is going to be very, very warm, and therefore there's going to be a lot of precipitation. As you go farther and farther north, however, the temperature gets colder and colder and colder. Therefore, there's going to be differing amounts of precipitation. Elevation, what is the altitude? For example, if we start at sea level at Ecuador, which is on the equator, that's why it's Ecuador, it will have a tropical rainforest at sea level. But as you go farther and farther up, you will actually they can actually get into tundra and taiga, where you go into all the different realms of the different types of biomes, because there are different types of climate because of the change in elevation. How close are you to bodies of water? Well, what causes the difference in temperature of the water is what are the ocean currents. The ocean currents at the sea surface are influenced by the air temperature and the wind. Deep currents are affected by other things, which we'll go through into another. Now, the things you should notice here is that they start out at the equator as very, very warm, and they travel all over the place up to here. Well, there it gets cold, and then it travels at the bottom of the ocean back down until it comes back up. And so it circulates, and this circulation is all about redistributing the moisture in the atmosphere. Now, one of the things that we're going to be hitting later on is this area right in here is called a gyre. And a gyre is where out in the ocean it just goes in a great big huge circle. And unfortunately, that is where a lot of plastic is, where it's in the Great Pacific Gyre. Now, there's two types of currents: of the surface surface current I said before, and the surface that's only about 10% of all the water. Vast majority of it is down below that. Below 400 meters is where 90% of the water is, and that's where the deep currents are. So how do they work?
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres. And because water holds on to heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow, or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted to survive in these swirling seas? Take a closer look at some truly
So water also moderates hopefully you now have a better understanding of currents. Water moderates because water does not change temperatures, which is kind of the lab you're doing today with the albedo effect. It moderates, keeps water, this area right in here, same temperature. So basically it's 64 degrees here during the summer, but in here the same day it's 93. Why? Because this is close to the ocean. Here, this rises, the temperature rises and decreases very rapidly. So, closeness to the water has something to do with it. Also, what is the temperature of the water has huge effects on it. For example, in San Diego, the temperature, like what it is out in LA, of the ocean currents, the surface currents, is very cold. Whereas if you're in Savannah, Georgia, they're very, very warm. And because of that, it changes the climate. Even though these two are at approximately the same latitude, San Diego's climate is like this, whereas Savannah, Georgia is like that. Why? Because of the surface temperature of the ocean. And that is basically what you need to know about climates and the causing agents of climates.